All right. So you did 15.5 and 15.6, right? Or just
Yes, that's correct.
okay, cool. Because I just figured you would kind of get into that. I did a multinomial ordered regression, but
Okay.
apparently using a national election study, which has like 30,000 people, which is one of the examples that they had in the homework. It took forever. So
Oh no.
I ended up having to like just take a small sample, but anyway, we'll get into that.
Yeah, small sample work. We're not trying to do real
Yeah.
analysis. So
Well, anyway, I had to let it run the first time for like about an hour. Got
oh
enough.
no.
Yeah. Okay, well, just real quick, let's go ahead and this will probably be a shorter day just because we're wrapping this up, and some of the stuff, I mean, I didn't do problems for, I just, kind of thought about sort of the conceptual stuff. So last week we talked about this idea of count variables, which, can only be zero. They can't be negative, obviously. These are events that we're interested in studying in a certain period of time and place context. Like, so we talked last week about this idea of the process being stable, which is noted by something called lambda, which is a constant for number of occurrences that we would expect. So yeah, and then talk a little bit about distributions for different types of lambdas. If we expect 5 events or 10 events or 20 events, these are the or for like this sort of the typical expectation. So Poisson models are sort of the standard count model that we might deal with, but if we have something called over dispersion, that means and by the way, in Poisson models, I think I said this last week, so Poisson models, the mean and the variance are typically seen as being equal, right? There's this expectation that they're not different because there is no proper sort of sigma. But if we have some level of variance that goes beyond that expectation of 1-to-1, then we might be it might behoove us to get into using what's called a negative binomial model, which deals with things like over dispersion. One of the things that we didn't really get into last week, although it is covered a bit in the book, there's actually like kind of too much stuff in this chapter. It's kind of hard. It jumps around a bunch.
It does. Yeah.
Yeah.
I think they're trying to jam a bunch of stuff in here before they switch gears to the next chapter, which is
yeah. So I finally that's why I took like a more of a protract. I just was like, okay, we're not going to do all of these, but we'll do as much as we can of good examples. So anyway, yeah, there are these things called tests for over dispersion. The book talks about them as like well, I use a test, something called the Brandt test last week, which there is a package, the AER package here. It's a dispersion test. This will tell us. I'm not going to run it here because I haven't run the stuff above, and
okay.
I don't want to like crash my session because it took me like forever to get this model below that multinomial model to run. So yeah. So anyway, last week we went into a couple of different examples of this, and then I won't kind of revisit that. So where we left was we finished up kind of negative binomial Poisson stuff. We talked about also yeah, so this idea of zero inflation is another sort of issue.
Right.
We didn't really we talked about it, but we didn't really do an example. And this would be one situation where an account situation, which by the way can happen quite a bit in medicine, where we have more zeros than we might even, that might be expectable based on, what the distribution is and all that. So this happens a lot in, like, here's an example in medicine, like whether or not somebody, actually how many ventilator days somebody has when they're in the hospital, like how many days are they on a ventilator? Well, a bunch of people are on ventilators, right? So a lot of times that the number of zeros is greater than what would be expected. So we have to use some kind of zero inflation. And there are zero inflated Poisson models, zero inflated negative binomial. I mean, there's a bunch of them, right? And so we didn't really get into that, but that's one of the other things. Besides over dispersion, we would want to check for zero inflation, those two things. And depending on how much, if we have either or both of those things, that would have a huge impact on whether we use a negative binomial Poisson or blah, blah, blah. So that's that.
I mean, one thing I wanted to point out, I thought about a little bit after last time, is this like zero inflation thing. Like when I was doing my some analysis of like sales numbers, it made intuitive sense that you'd need like a two-stage process. First, was there was this a day where there is sales? That's some probability ratio. And if it was, then the sales are Poisson distributed. And that's basically what a zero inflated Poisson does. And the same thing true with the negative binomial. The negative binomial is just a convenience, right? You could use anything, but it turns out if you use a gamma distribution to select your probability, your rate from, and then use a Poisson distribution, that's actually equivalent to a negative binomial. So that's just something I learned the other day. I just was reading up on that. I'm like, oh, I see. So that makes more sense from a data generation modeling point of view. That's the model. The model is that there's, we don't, the rate itself fluctuates, right? And that'll cause the dispersion to increase, right? That'll cause the variance to be different than you expect from a binomial where the rate was fixed. So
you're thinking about it deeper than I thought.
Well, I don't like the
distribution thing. I hadn't thought about that. Yeah, that's
it bothers me when they just pull stuff out. Oh, we'll just use a negative by why? What has nothing to do with the negative binomial the way the way it's normally defined. Like it's defined as like the first how many counts do you get a failure or something, right? It's like, what does that have to do with my problem? Nothing. So this is what it has to do with. Right. It's the idea of adding some kind of variability to the probability or the rate
parameter,
and then if you happen to use a gamma, which by the way you could use anything, but if you happen to use a gamma for that, then it turns into a negative binomial, and that's convenient. After all, we don't really know what that underlying distribution would be, so might as well use the gamma, right? And then as long as it gives you, it's a perfectly good model, right? It's kind of like what we did. Remember when we did the binomial? Remember a long time ago we did the what do you call that? Conjugate priors, right?
Right. So,
why would you use a beta distribution for a prior for a binomial? Well, because it's convenient. We don't have any, we can make any kind of shape we want, more or less, to what degree of understanding we have of that prior, which is not much. So might as well use a beta, then we can get a convenient posterior, right? So it's kind of similar to that kind of point of view, isn't it? It's like, this is a convenient thing to use the gamma. If you use a normal distribution, you can still do it with Stan. You can still use a normal distribution and then feed it into a Poisson. That'd be a perfectly legitimate model that you could write in Stan, but you couldn't do necessarily in I don't think R Stan R would support that, but you just do straight full up R Stan, right? We haven't done any of that. I haven't done any of that. I did a little bit like a year ago or something, but now I've forgotten how to use R Stan, raw R Stan.
Tell me about it. So the story of my life is, you had a good experience learning something, and then you just don't pick it up for a year, and then it's like, well, that's one of the reasons why this class or this, this group is so, groups like this are important. At least to get you some additional kind of just picking some ideas up and playing with them.
Yeah, I sorry, I just wanted to share that. I think
that's cool, man.
It was bothering me. It's like, because in the book he just says we're going to use a negative binomial, and it's based on some sample distribution. We're not going to go into that further. Just like, wait a minute. Go into it further. What is wrong with you? I got a minute. Tell me.
Well, like 5 years ago when I was doing this, I used to work in neurology, and there's lots of like, length of stay, which is another count. How many days you were in the ER or in the critical care or whatever, or in like in emergency room or whatever, the critical whatever. And actually at one point I did read like a very long book distinguishing the two, but of course that was like 5 years ago and I can't remember it now. But there is a lot to the difference between Poisson and negative binomial. They don't go into great detail on this. And also, I'll be honest, like one of the things that's kind of throwing me in all of this stuff is because we're doing this all in a Bayesian framework, a lot of the stuff that I used to know how to do for count models and stuff, and how to visualize and how to interpret and stuff is a little bit different. So actually I had some issues, but before we get into that, let's talk about probit models, which is another.
Sorry, let's get back on track. And by the way, talking about interpreting things, I just want to point out that the next section of the book is seemingly more focused on that issue of interpreting and causal all that kind of stuff.
Yeah.
So I'm looking forward to that.
Yeah, that's I'm interested in that. So yeah, program models are something that like I probably spent like very few days on in graduate school, just because once again in biostatistics and medicine, logistic models are typically what. But I mean that being said, I'm sure there are fields and subfields that kind of focus on this. I haven't done much with this as of late. I do know that I think probit models are used for like dose response type of analysis,
Okay.
in medicine. So that might be something, but I haven't done it. So anyway, a couple of things. What is it? Okay, the probit model is the same as logit, except it replaces the logistic distribution by the normal. The only difference being between the two that they have this latent error distribution, which can either be logistic or unit normal. Yeah, and so of course, logit models are a form of model where we're trying to predict the probability of something happening. That's typically dichotomous, yes or no. And if we were to play out, sort of like the odds ratios of all that, we would say that logit models are used to model the odds of the success of an event as a function of some group of one or more predictors. But the probit is used to determine the likelihood that an event, item or event will fall into one of a range of categories by estimating the probability that observation with specific features will belong to it. So, by the way, I obviously copied this in like verbatim.
Yeah.
Do you have anything else you want to add to this? Since obviously you were, you kind of took on some of this stuff.
Yes.
Also, you probably want to share your screen too. So.
Yeah, you want to work on do that exercise right now?
Yeah, let's go ahead. As we hit them, let's just do them. Yeah.
Okay, hang on one second. Let's keep that going. Let's see. Oops. Yeah, that's probably because I did have some questions about that. I'll just do. I'll do it in order rather than rambling around here. Let's see. Where is it? Chapter 15. This will probably work. Just going to share my art studio. Good, right?
Yep.
Can you see that? Okay, hang on a minute. Okay. So 15.5 was actually relatively straightforward. The idea there was to just to compare the logit and the probit, right? So we're going to take one of the data examples from chapter 13 and 14. So I looked through the chapter 14 exercises, and I found this rodent data set.
Yeah.
And there's a whole bunch of columns. I didn't look through. I mean, there's a little document there that describes what they all are. Kind of just did a quick run through that. And the columns they picked out of there were rodent, which is the indicator variable 0 or 1, if there's a rodent or not. The persons per room, which was a double indicating how many persons per. These are for buildings essentially. There's also a neighborhood level.
So hold on. That's how many rooms there are. Is that what we're saying? Or like
the inverse of that, how many people per room.
Oh, okay.
Like an apartment building or something, right?
Right.
Whether it's dilapidated or not, run down, I don't know what that meant exactly, whether it's below the poverty level, whether they had a recent extermination. I'm not sure what the G part, I forgot what the G part was for, but anyway, whether they had an extermination treatment recently, whatever that means. And then there's another one that most these are 0 1s except for race, which is here, 1 white, 2 black, Puerto Rican. I don't know what they call that out. I don't forget what this is, so that's probably the reason why. Hispanic, Asian, Pacific Islander, Indigenous.
Yeah.
I changed it to Indigenous. It actually says something else, but my Canadian friends prefer Indigenous. So
Got it.
And then 7 was 2 or more races. So that was they actually wanted us in the actual problem from chapter 14. They first wanted you to do a focus on the race, but hey, I just did pulled all that stuff in, and I did the standard logic first. I just used everything. I wrote it out this way because I needed to make sure the race got factored properly, but
Yeah.
there's probably a better way to do this.
But sorry, I didn't. So what's how many rows do we have here? What's the size of this data?
1748.
Oh, okay.
It's not super big, I don't think.
Wait a minute, hold on, go down. So the number of people
Got the-
per room, so there's like 1.33. Is that like, what is that? Like counting like
So it's like an apartment room building, right? So
oh, so this is the average. Sorry,
yeah,
excuse
on
me.
average, yeah.
Got it. I was like, are they counting in 0.33 as like an infant or something?
No.
My bad.
So so the standard logic, I guess I can run this. It won't take very long. Hopefully it works now. You know, just using link equals logic prior. Now, okay, I put prior equal to null here to use a flat prior, and that it's not because I'm trying to you know, reproduce a maximum entropy fit. I just, there's a reason for that, because when I try to do the logic, the probit, it didn't work. And I looked online, there's like some bug apparently with the stand GLM.
Mm.
The default priors don't work well with it. It doesn't, you know, because I guess because it's, you know, narrower or something, but surprisingly, I mean, you wouldn't think a factor 1.6 would matter that much, but anyway, it would crash. So I read online, somebody said it works fine with flat prior. I'm like, well, flat priors it is, that's fine for this. So I'm not going to dig into why it doesn't work. And somebody said if you write it out with RScan, it works just fine. So it's not clear what's going on. So it's a bug, I guess. Anyway, there's the fit. Here's all the coefficients. We don't need to spend we don't spend much time on this because I'm not really here to interpret these coefficients. Rather, just trying to compare the logic to the probit, right? We do see there is some big factors of race, and there's some.
So those are all log odds, right?
Yeah, these are all log odds. Yeah, which is nice because that's the advantage of the logic, right? You can directly interpret these things as log odds or as effects.
Well, I mean, I like to as you know, I like to exponentiate them.
Yeah.
But yeah, other than that, yeah, I mean, like, yeah, you're right. This is easier.
Yeah. So dilapidated didn't seem to actually have a significant effect. If you look at the standard mad standard deviation there, but which kind of surprised me. The biggest predictor probably is this, you know, race of all things. So, which I mean, that to me, that means that there must be something else, because that's no reason why that would make any difference. So,
can you remind me again what the outcome is? So it's whether or not they have rodents or something?
Yeah, whether they have or not they have rodents detected on the subsequent visit, I guess. Or,
yeah.
So anyway, that's the fit using the logic. Then we fit it using the probit. So the only thing different here is I put link equals probit. And again, if you don't have this product of null, it doesn't work. Don't know why.
By the way, just can we go back to that real quick? So if we exponentiate the dilapidated thing, now I don't know if you can even interpret it as significant. Well, I mean, I shouldn't even use the word significant, you know, but if we exponentiate that, we get 1.2 basically. So we're basically saying if it's dilapidated, there's like a 20% increase
with the big odds.
Yeah. So, but you know, once again, that's, I mean, if anything, the person thing looks like it's got to be significant. Yeah.
Yeah.
So, okay, hold on. So let's.
And it is.
So basically, okay, so that's the odds ratio is then, the odds are then, 2.21. So basically, if for every, actually, I don't know, maybe it depends on how the variable is set up, right? So is that like, are we saying for every single person that increase, is that what we're saying for the log odds?
Yeah, that's right, yeah.
Because if you exponentiate 0.793, you get 2.21. So you're basically saying there's for each additional person, you get an increase of 120% odds of there being rats. I guess that makes sense.
Yeah, because it's more crowded. It makes sense. Yeah.
Yeah. Anyway.
Actually, while we're here, maybe you can help me understand like how you interpret this. So, right. So like I put this factor in here, right?
Right.
So race 1, which is white.
Yes.
So none of these would be true, right?
Right.
And everything else stays the same. So it's saying if you're black, you have this huge increase in the log odds. Why would that be? I don't. That didn't make no sense to me. I feel like there's something. One of the other columns, I guess, has got to be controlling for that. Poverty is not it.
So what's 3 and 4?
3 is Puerto Rican, I think.
By the way, I did the same thing for
Puerto
mine
Rican.
because I couldn't figure out, like, I couldn't find like some of the variable, like I didn't know what some of the numbers meant, so I had to look up like my own.
3 is
Okay.
Puerto Rican, 4 is other Hispanic, 5 is like East Asian.
Okay.
Islander.
So relative to white.
Yeah.
Okay. Yeah. That's basically what that's what we're saying here. Obviously the intercept we can't really interpret because it's negative, but
that's for 0 persons. That's for a white person with no people in the room.
Right. Yeah. So they're even though there's nobody in the room, they're still white. Yeah, I like that. I like that. I like how we have to like label
I guess the right way to do it would have been to standardize that particular variable.
Right, like to do like for,
or at least center it
for the mean number of people.
We just subtract 1 would have been good even too. So at least you're starting with 1 person.
Yeah, that's true.
Increase over 1 would have been better.
Right? Yeah. Well, c'est la vie. So apparently, basically, what we're saying is, well, yeah. I mean, it sounds like for certain races and the number of people, those, or actually, no, excuse me. Then the number of people, those seem to be the 2 most kind of practical things.
So anyway, there's probably if this were a real problem, you'd want to investigate what's going on. And the first thing you would do with this real problem is go through and look at the rest of the columns here. There's a lot more columns, like what floor they were on. There was other levels of poverty in there. Besides, there's like under twice the poverty level is another one. So it deserves more investigation. I mean, obviously, this is not a scientific study. This is just looking at the probit versus logit, right? So we do the probit fit, like I said. It does work if you put prior equal to null. It doesn't, like, I guess that somehow if you don't have prior, it's still slower, by the way. That's which makes no sense. I don't know why. It's just a slower process. See, it's still running.
Yeah.
And you get, smaller numbers. And well, are they 1.6 smaller? That's what the hypothesis is, right? For probit comparing, you can.
Oh, right. Yeah.
So if I take these B fit and multiply by 1.6, right, to see if they're basically the same, and they basically are the same within the errors, right?
Yeah.
Within the errors, yeah. So that's what I guess that's what you'd expect from what when you compare the probit and the logic. And so the next problem was, okay, fine, come up with something where that doesn't work, where the probit and logic give different answers or different answers beyond a factor of 1.6. And I tried a lot of different ways to do that. I tried so basically my approach was to start with some X variables that are randomly distributed, right? From -1 to 1. Then do some kind of linear model on that, 5 times X, and then add some Z here is I'm using this latent picture, right? So I can control better, what the model looks like, right? So I'm going to create this latent Z, and then just my indicator is now is Z greater than 0, right? So I tried a lot of things here, right? So I'm just using a normal distribution here because I tried like Cauchy distributions. I tried all kinds of things here. I tried to make because it says something about the tails. There's some points in the tails that causes problems with this, right?
Right.
So I put points in the tails with Cauchy. Finally, I just went back to a normal distribution. So this would be a probit model, would be better for this, right? If I fit a probit model, I ought to get 5 here, right? For the fit. Except now I messed up. So I thought I'll mess up a different way. I'll flip some values out in the wings, right? So out the tail. So that's what I did. So that, this thing doesn't quick.
Man.
So this is my model, right? So like it should switch over here, but I threw some like outliers in here. So this, this one doesn't fit the model. This one doesn't fit the probit or logic model, right? And I tried a lot of variations on this. And the reason why, because even this doesn't really make that big, it doesn't really satisfy the vastly different. If I fit it with the logit, it gets, strangely enough, those outliers, the logit actually finds the X equals close to 5 better. I don't know why. That's I think that might be a coincidence. And then you do the probit, which is actually the real latent model here. It doesn't get the right answer for X, for the slope on X, which was 5, right? Because it's not really that's not the right model anyway, because they threw all those extra things in there, right? I screwed it up on purpose by toggling, the Y values out in the wings. And now we can compare them. They still don't compare that badly. I mean, yeah, that it's, just barely outside of 1 standard deviation. I could not get any more of a difference between these 2 coefficients than this. Everything I tried, comparing the probit to logic with a factor 1.6 is pretty robust to try to screw around with it. And yes, if there's things out in the wings, it is somewhat significant, I guess you would say.
Yeah.
Just about 1 standard deviation difference between the 1.6 times the probit and the logit, which is probably more than you would like if you're doing a lot of modeling. But I guess my conclusion is I just don't know what. Here's what the comparison of the 2 models are, right?
Oh gosh.
Hardly any compare. It's hardly any different, right?
So red is the logit though, right? Or
red is
yeah.
Red is the logit. Yes, you got that right.
Yeah,
because it's sharper.
Yeah.
Red is the logit, but you wouldn't say that one of these models is better than the other one, right?
No. I was just trying to guess. Yeah.
But the point is, these models are very close, and even though I tried really hard to make the 2 models different, by throwing in extra outliers way out in the wings, I couldn't. I don't know what the right answer to this problem is. I don't think I found it.
Wow.
So if anybody's ever watches this video, and feel free to ping me with, "Hey, you dummy, what you should have done is this," because
Yeah. Well,
my conclusion is that, hey, you know what? It doesn't. I guess my conclusion is probably not correct, because people have been using probit a lot, but I don't see any reason why you would ever have to use the probit model. Stick to logit. It works better. It gives you log odds. It's interpretable. I don't know.
yeah.
Unless your latent variable really means something, which is different, right? In that case, that could happen, and that'd be a different situation. But
Okay.
because there might be some other predictors based on that same latent variable, then you have like a different kind of picture.
Yeah.
I'm probably wrong about that, but that's my
Yeah. No, that's
55,
good.
15, 6. Cool. All right, that's my my turn over.
That's
my go at the wheel
your story, and you're sticking to it.
Yeah.
Okay.
Any comments on that?
I mean, yeah, I guess I don't know. I'm still just trying to figure out, like, I'm still not quite sure, like, when do I mean, I appreciate the work to try to find how similar they are, but I guess the question is I'm still kind of I need to do more digging on myself on, like, when do we need this? When do we
So far all I came with is never.
Yeah. But there are, like, people in certain areas of statistics who do probit, religiously for, I don't know. So yeah, I guess I just, we need to, like, get into this more. But that's fine. I mean, that's not neither here nor there. But there's also not that much coverage of probit models in this chapter, so I don't think we can.
I've never really run into them.
Yeah. So basically what I did was focused on this idea of ordered versus unordered categorical regression, which can be anything from people calling it ordinal regression or ordinal logistic regression, or if it's unordered, then multinomial regression. So I only do an example of a ordered one below. Well, actually, I did it ordered based on political parties, and that's kind of what they did that's what they specified in the example. But you could also say, they're not ordered. I mean, I don't know, I guess, whatever. But yeah, so one of the things that kind of tripped me up a little bit here is, so when you do this like in a non-Bayesian thing, one of the things you kind of are concerned with is doing what's called a proportional odds model. Are you familiar with this concept?
Only from this chapter.
Do they actually? I don't know. Did they actually make mention of it? I don't know.
Oh, I'm sorry. I thought you were talking about. I thought you were just referring to what they did in this chapter with the with the
typically
variable.
When you have like an ordered outcome, like where it's like, okay, let's say the outcome is like a Likert scale where the lowest response is never 2 is once in a while, 3 is sometimes, 4
Right.
a lot, and then 5 is always. So one of the things about doing ordinal outcomes is that you have to sort of assume that you're meeting the proportional odds assumption, right? Which means, as I say here, the event being modeled is not having however there is in a particular category. So basically, what we're trying to say is does the effects of all of the predictors, is it the same going from the lowest to the second lowest as it is going from, let's say, the 4th to the 5th, right? So the impact of the predictors the same across all ranges of across all aspects of the range of these ordered categories. Does that make sense? Because
Right.
if not, then we can't really do this type of analysis. Maybe we have to collapse some categories or whatnot. So yeah, so in
So
proportional
this
odds
is not the
models.
same as the method they use in this book where they have that, they use the latent variable.
Well, right, yeah. So
It can be the same, I guess, because they don't assume the odds are proportional, because one could
I
be
don't know,
the
and I guess.
cutoffs could be anywhere. Those C1, C2, whatever could be anywhere, right?
Well, right, but remember the cutoffs can be anywhere, but you're still assuming this idea of increase,
Yeah, increasing,
the
increasing.
range. So I guess,
Monotonically, yeah.
yeah. So that's the only reason I even brought this up is, I mean, once again, I'm not saying this is what they're doing in the book, but like this is what I learned. It was the proportional odds model, which I wasn't using Bayesian sort of models or anything like that. I was just running, frequentist regressions, and
Right.
yeah, and so basically it's essentially means that the predictors, if we meet this assumption, the predictors have the same effect on the odds of moving to a higher category everywhere along the scale, right? So if is the effects of gender or age or whatever the same, moving from level 1 to level 2 as it is from 2 to 3 and blah blah blah. So one of the other things, it's sort of obvious, but if we were doing an unordered or a multinomial regression, we would use the M-logit link function. But since we're doing ordered, we would do C-logit or cumulative logit. Yeah, so basically this was the example 15.4. So this is the 2000 national election study, which, like I said, the original sample or the original study says it was like 37,000 people. And I didn't even get, well, I didn't get to the binned regression thing, but basically one of the things I should say is that they actually had originally 7 categories: strong, weak, independent for Democrats and Republicans, and in the middle we just have independent, right? That I tried to fit that, but that just was like taking so long, so I collapsed it into just Democrat, independent, and Republican. And so unfortunately, when we had all 7, and by the way, I randomly sampled 2,000 observations.
Okay.
Without replacement, obviously. But yeah, when we used the whole sample, it was a lot more, but whatever. Yeah, so here's a couple of things to know. So like you can like I was tempted to try to do this multiple ways, but this took like 10 minutes to run, so I wasn't able to. But it seems like what a lot of people do is, in terms of setting the priors for something like this, they're not setting the priors for like what they expect each level to be, or or whatever. Like they're setting the prior for R squared, right? Does that make sense?
Yeah.
So
no, I mean, I know that's what they're doing, but I didn't really understand that part of the book to take you. Kind of
so I guess you're assuming that the overall model relationship will be 0.3, I guess. I'm assuming.
Right. It's plain variance,
Yeah.
whatever. Yeah.
So anyway, yeah. So what I did was, so remember, we're trying to predict like what the party voting is, like what party are you affiliated with, right? And so they had a bunch of like things, and just because I didn't have a ton of time, and also because I didn't want to add too many things, I just picked age. They have dummy coded for female, and then I just used the white dummy coding, which just because I figured, well, we knew, going from Democrat to Republican, that would, probably be, an impactful one. So
Yeah.
at least based on,
Yeah.
not speaking of personal affiliations, I'm just saying like in general. Okay, so one of the things I really had a hard time with is because we're not doing like these aren't odds ratios. And he keeps talking about them as like these median estimates or whatever. Sorry, I need to find this in the book. So I spent a lot of time trying to figure out how to really interpret these things. It just I only got today and a little bit of last night to work on it. So maybe I'm just missing something, but okay. Right. So you mentioned this idea of latent variables. So yeah, talk about the three parameters. In terms of the parameters are the cutoffs and obviously the standard error. And so in this case, there's a cutoff, at 1.5 and one at 2.5 for whatever this example is. But yeah, like it's not really clear to me, like, okay, so like for example here, well, this is also, well, I don't think this is the same data set, but so we have a cutoff. Once again, I don't really remember, like, but I'm still trying to figure out, like, how do we interpret this 2.72? You know what I mean? It's not an odds ratio. So
Yeah, I don't know.
yeah. I mean, basically,
there's the cut point, right? Cut point in the odds ratio. I don't know how you.
Yeah. So basically what we're saying is that there is a greater odds of moving from 2 to 3 than from 1 to 2, right? I mean, that's kind of all I can really think of. Yeah, I mean, this is probably the part I'm least satisfied with the chapter, because it's like they just kind of talk about this, and if we want to transform them, we need to linearly rescale them.
Ryan, I just skimmed over this part. I assumed you would explain it to me.
Well, I kept trying, man. I know.
I'm with you on that.
I know.
This is one of those sections where I'm like, if this ever comes up, I'll come back and do it again.
Right. So we prefer because we're going to directly interpret as thresholds on the scale of X, right? And okay, so on the scale of X, but okay, so the scale of X here is value, I guess, which I don't know what value stands for. Obviously, if you have multiple variables, yeah, so unfortunately, I don't have a great answer here, but one of the things I did do is, of course, I used my beloved plot underscore model thing. And one of the things this shows us is,
cool.
Well, first of all, being white, you're more likely to be, I guess, well, now that I'm thinking about it, so like,
what was the predictor again? What was the outcome?
Oh, it's whether you're Democrat, Independent, or Republican.
Okay, right.
Ordered it from Democrat through Republican. So I'm assuming, okay, so basically, I think it's like I think it basically means white people are more likely to be Independent or Republican than Democrats. I think that's what we're saying, right? And then, we have a stronger odds ratio going from Independent to Republican, right? So, but how to interpret this? Yeah, I don't know. And then I started working with this, but this was from the book, but I never got around to it. But yeah, so I don't know. This confused the hell out of me. So we have odds, we get odds ratios from this. So I'm assuming, like, okay. So I make sure I'm clear. Okay, yeah. So the odds ratio for 1.1 is 3, which is, where we are here, basically. And yeah, but yeah. So what was interesting to me, well, first of all, actually, also age doesn't really pop up here, because I think it's just such a small thing. I should have divided this by what, like 10 or something like that, I guess. I'm kind of tempted to want to try to rerun it, but dude, it took forever, so I can't
Yeah.
really do anything. But so anyway, yeah, obviously I'm still a little bit confused because, well, I don't understand all of these things because we're not doing proportional odds. I'm a little bit confused, but I think what we're saying here is the impact of moving from independent to Republican is more likely than moving from Democrat to independent, I guess. But other than that, yeah, that's all I got. So, and that's as far as I got, because like I said, I was going to try to do more stuff, but I ran out of time because I had to scramble to get like some sample that, that would work. I really wanted to use the full. Actually, I don't think there's any kind of like parallel. I don't know if any things that you're using with Stan, that some of these things have like arguments where you can like do a parallel processing thing. I don't know if that seems to make a difference for me.
Oh yeah.
But anyway, so yeah, I'll have to leave it there, unfortunately. But
No worries.
but
I mean, I'll
basically,
be honest with you. I'm not even kidding. I really did my eyes kind of glazed over during this order.
well, yeah, there's just, and also, well, actually, also one of the other things, and I was gonna, once again, this was gonna be the other thing that I did, which is this idea of robust regression, right? Which
right.
I always think of coffee every time.
Robusto.
Yeah, like Robusto, so it's always kind of funny to me that like this idea of robust, it has like kind of like a flavor connotation to me. But I guess, yeah, the basic gist is using the t distribution instead of the normal distribution as a way of dealing with those kind of like tails, right, being weird, I guess. So yeah, that was about all I got, and I didn't even really get a chance. Actually, this isn't exactly what I do, but yeah, like I do what's called discrete choice analysis or models, where we are looking at like multinomial attributes and looking at how likely that would be for someone to choose something. But anyway, I'm rambling.
Do you do ordered stuff a lot, or do you do more unordered?
I
Standard
haven't recently, just because well,
it's kind of interesting. Like, is there an issue with, so in ordinary, like non-Bayesian, it's pretty standard to do like a softmax multinomial thing, right?
Yeah.
Or in any other machine learning model. But in a Bayesian picture, this is twice now the two different Bayesian books that we've gone through, that when you get to multiple categories, they kind of punt a little bit. Right here, they talk about ordered, and he kind of like shoves aside the unordered, and which seems to be the more common case. And then in the Bayes rule book, you remember that when we did the multi-category, they just like we did a side tangent into naive Bayes instead, and like which is kind of funny too. So there must be some challenge. I meant to look into it, but some challenge to doing a multinomial softmax type thing in a Bayesian way. I did Google it a little bit, and I found they led to complicated things. So I suspect that there's truth. There is some challenge to it. I meant to look in BDA, the BDA book, because that's Gelman's big book, right?
Right. Oh yeah. The
BDA.
The hierarchical models one, is that what you're talking about?
No, Bayesian data analysis.
Oh, yeah, actually, no, I don't have that, but I've seen that.
But it is available online for free too. But.
Yeah. So next week we've got chapter 16, which I'm gonna let you take the lead on this.
Yeah. And
I guess I actually, one of the things that I did like, I mean, obviously it kind of is, it's nice for me because it takes some pressure off of me, but also it kind of keeps the non-leader engaged. Is I was going to take one or two of these problems
in chapter 16,
but like, I could do 1610, I guess. I don't know if that would be of interest.
I haven't looked at any of those yet. So 1610, sure.
Okay, let's do that. So I'll highlight this one.
You pick on 1610, and I'll do something else from that chapter.
Yeah.
And go
but
through
I'll
highlights. We'll do the same thing. I'll kind of go through the highlights of the chapter. We both have read it, so we don't need to talk through the whole thing. I think we should do that for the rest of the book, by the way. Just like kind of highlight what the main things you got out of it. Then we can do the most important thing, which is talk about the things we have issues with. right?
Yeah.
And then if we decide we need to come back to it the next week, we will, right? That kind of thing.
Yeah. I think that's right.
Especially this last few sections, which are going to be like more, some ways more interesting and more important, but also more challenging in some ways, right? Because they have to do things like, imputing on missing variables, values, and interpreting causal, right, inference. And
yeah, we only have like 5 more chapters,
Yeah.
which I mean, I guess that's actually a lot depending on how you think about it, but
Yeah.
I don't know. I think it's pretty nice.
Yeah, we got missing data. Oh wait, that's the wrong book. wait. This book I'm not looking at the wrong book. I'm looking at VDA3. I was trying to go search through VDA3 to see if there was anything in there about multinomial, but actually, 105 things. I don't know. Oh yeah, that looks like a hot mess. No wonder they don't want to go.
Yeah.
All right. Anyway,
Well,
all right. So that's great. Let's pick this up next week. I will prepare chapter 16 and I'll look at some problems to hopefully are interesting in there, and on we go.
all right. Sounds good, man.
Yeah. Thanks, Ryan.
See you next week. Bye.